Hello and welcome back to differential equations. I have to unmute myself in Zoom. There we go. This is section 2.1 on population models. The lecture that will fill in the blanks for what we did in the past with the separation of variables. So you had the population model. I'm going to call it the old model as P of t equals P0 e to the kt, and we said that that one was bad on the long run, right? So the old model was good locally. If you have to look a couple of years ahead, a couple of years in the back, and so on, its exponential model is pretty good. But if you take the limit as t goes to infinity of your population model we have, turns out to be infinity because basic exponential function graphs this way, and you can see going to positive infinity up there in population, and your p0 would be right there, time t in years. So not a good model overall, not a realistic model, because you cannot keep piling up population and people or rabbits, I don't care what, infinitely past certain point that habitat can sustain. In our case, is the planet, which has limitation, space, right, surface area of the planet, and then in terms of the what do you call the resources. You know, you have finite amount of resources and finite amount of food and minerals, fuel, everything that it's that we get in the ground or grow on the ground. All of that stuff is finite. So going into this model, we understand that this model is good for local calculation. So if you just want to look at, you know, a small part of the curve, then yeah, it all makes sense. But if you try to, you know, go far in the future or try go far in the past, you have big discrepancies from data, or your predictions are not going to be good at all. So we are going to take a look at the better models. And now, before we do that, we just need to one more time say for this model the P0 is initial population. And this is not going back to the beginning of time. It just goes back to the point where you want to start to measure from. So if I say there are no rabbits on this island and then I toss 500 rabbits to that island, it's going to be 500, and then P0 equals 500 because that's when I started measuring. And then we're going to take that time equals 0 is 2020. And then we're going to see at t equals 1 is going to be 2021. T equals 2, that's 2022. So we are going to set ourselves the goal, right, where we start. Sorry, we're going to set ourselves the starting point and then run towards the goal forward in time in terms of population. Now, you could go back as well. And as I said, depending on how good the model is, it might do a very good job on verifying the data that you had before. Now, constant k is the rate of change of population. No, that's not the rate of change of population. That will be the derivative. Is the growth rate. There you go. Growth rate. And p prime of t would be the rate of change, which is basic calc 1 derivative. Rate of change of population in time. So you can do your differential equation, like P prime equals Kp, right? Now this K is very important, and most of the time you spend figuring out that K, because K is in some sense the carrier of the whole model. If K is positive, population is growing. If K is negative, population is decaying, meaning the population is decreasing. And the K also depends on the conditions in which, so in this basic model. So is there enough food? What's the situation with predators? And also male to female ratio is also impacting K. That's actually very good exercise to take a look at K. Let's say that you put 100 male, 100 female, and the pairs can only produce one offspring. And it takes, well, in the case of humans, takes about 9 months to cook up a baby. So if you take a look at, let's say, we're going to take a look at per year, right? So 100 male, 100 female. So that's going to be 100 couples. And if you have 100 couples, they're going to produce 100 offspring. And then I'm going to use the word offspring because you can think of this as rabbits or people, I don't care. Obviously, rabbits have way more than one, but let's say it's just limited to one. So if this is 2020, then in 2021, you're going to have 300 units of this population, because you still have original 100 of male and 100 female. That's 200 units. But then you also have another 100 of the offspring because you had 100 couples. So you have 300 population in 2020. Now we're going to switch this, and we're going to say the same 200 population, but we're going to put 199 male and 1 female. Now remember, the female is going to pick an alpha from here, because that's what happens. So you only have one couple, which produces one offspring. So now, in this case, in 2021, you have 201 population. Original 199 male, 1 female, that's 200, plus 1 baby, or baby rabbit or whatever. And now we're going to switch this to 1 male, 199 female. Now it's very important that these females are not jealous, because now that's going to produce 199 babies, because this is going to be one very busy guy. And in 2021, you're going to have 399, right? That's 200 plus 199, 399 population. So you see that the rate of the growth of population depends on the ratio male to female. It's not just, I mean, if you put all male or all female, we said K is going to be 0 and the population doesn't change going into the new, given that none of the initial population dies due to predators or old age or illness, disease, or anything like that, right? So if there is nothing to kill these initial population units, subjects, whatever, then moving to the next one, if they're all of the same sex, then the population doesn't change. So that's K equals 0, which means the rate of change is 0, which means population doesn't change going into the next year. And then you see that if you put 100 male, 100 female, and you create 100 couples, right, then that produces 100 offspring, because each couple, we said, in a year, in this problem, like only one offspring. So that's going to be 300. And then if you change the ratio male to female, then you can see that the population is either going to be 200 or 400, right, roughly. So the K is very important, and K also tells you, all of these things. So availability of the food and, so in this, what we call the old model, like our first model, the pre-calculus model, all of those are mushed into a single, they're all mushed into a single constant K, and it usually doesn't work well on the long run. But in 2.1, we learned much better case, right, with this general population equation, which turned out to be logistics equation later on. So we are going to take a look at some setup. So before I'm going to put a big red title here, logistic equation, and we're going to build it up. So for logistic equation, we can actually introduce some of the parameters here and understand in which way this whole thing. So let's define a function beta of t. The beta is the Greek letter. This is lowercase b, equivalent to our Latin alphabet. The number of births. Per unit of population per time or in time, and delta t, which is a d for death, right, is the number of deaths per unit of population per time, per unit of time. But right, if you pick 1 year, then it's just, everything's times 1. You could pick 10, it's just calculations are a little bit more annoying. So if you take a look at that, you are going to get beta of t times the population in time times change in time, which could be 1 year. And that's for births. Oops. And then you have the rate of death by population, delta t, and that's deaths. So as the time progresses forward, it is common sense to say that change in population is the difference births minus deaths, right? Because everyone who exists on the planet had to be born at some point, right? And then they die. Very, very enthusiastic thing, right? The way you look at it, right? It gets born and then dies. Like, yeah, there is a little bit in between, right? We don't talk about that in differential equations. It's just, yeah, born and then death. That's it. So we have change in population equals difference births minus deaths. So change in population is going to be the equations we have go up there. So beta of t, p of t, delta t, minus delta t, p of t, delta t, right? Which simplifies into delta p equals, factor out population over here, and times, so you have your beta t minus delta t, p of t dt. Ship dt to the left-hand side, dp dt is equal to beta t minus delta t, p of t. So you guys now have the equation here, which shows that you have the change of population in time on the left, and that's exactly what we wanted, right? We want to study the change, so we have a differential equation. If I have a differential equation and I can solve it, I get a new equation for population, which should be way better than the one we had before. So now, this mess translates into dp dt is equal to beta minus delta times p. And this is the differential equation that we want to consider, which simply says that the change in population in time is proportional to the product of births minus deaths times the current population. Because obviously, without the current population, you can't have births, because those units have to give you new units. And there will be no death either, because those are the units who die. So you have to multiply by the current population that it's there. So now, in the next step, I want to introduce a couple of other parameters that will transform this equation into an equation that we want to use to solve this. So the thing is that the birth, as we observe in nature, birth decreases as the population of the world increases. More people are of the thought, well, I don't want to have kids because I want to have my own life and all of these kind of things. And it doesn't get pushed in a society, back on talk like that, because we are already overpopulated, so no one cares, right? We have enough people moving around, and having that kind of is not something that is crazy important at the moment. But if you have a smaller population and they live all close by, and one earthquake can eradicate them all, then they have a way different way of thinking. Well, we have 10 people in our population, so better increase that as soon as possible. So they have different view on the situation. But it goes for animals and people. The more population you have, there are less births, right? And that's actually good to some extent, because the resources are finite, right? In terms of competition for food and space to live and the habitat. So whether you talk about animals or humans, it really doesn't matter, because we don't operate very well in ice caps and deserts and water. I mean, we do have some people living in those conditions, but those are insignificant amount of people in comparison to the population of the planet. So, I mean, vast majority of the people do not live in those extreme conditions, and you would have to go long way to actually make themselves live there, right? So, we are talking about limited food supply, limited places to live at, and habitable, right, and all of that stuff. So, the observed birth rate decline is linear. So for large population, births fall off linearly. So you can say that your beta function is some initial number minus the constant at which it falls, including the, right, in respect to population. So there is the birth rate, right? We said this is the birth rate, and then it's going to have some negative slope there, so negative beta 1, times the population, which is the number of units that are involved in producing those births, right? Because it comes from population. And the death rate remains constant. So death rate is just going to be whatever value we had before. And now, when you plug all of those things into the values above, you get your change in population in time is going to be beta 0 minus beta 1p minus delta 0, everything times p. And now we can simplify this using some values. So you can use that A is equal to beta 0 minus delta 0, and the B is just beta 1. So if you do that, your differential equation transforms into, and the only reason, so I'm just going to say substitution, because the only reason we do this is to make it easier for us to solve. So we have less writing and less constants floating about. We can always, once we solve the equation, we can always go back and plug these things in for A and B and have those actual constants that you measure, because we have lists of people born, birth certificates, right, which are in records or town halls. And then you have death certificates issued by medical examiners and doctors and so on. So there are birth certificates and death certificates. So we know all of these numbers all the time. It's just that it's a little bit annoying to solve the differential equation having those floating about. So we simplify this into something like this, right? This P would distribute inside. So this guy and this guy make your A, and then times P is AP. And then you have your beta 1 is B, and then P times P is P squared. So that's just plugging things in. And then there you have it. This is your differential equation that we want to solve. DifEq we need to solve. Now, we can now use the basic separation of variables procedure and go through those calculations. So we have a dp over ap minus bp squared equals to dt. And we just follow the situation. I believe we already did this when I did separation of variables. We didn't do the Newton's law of cooling, but there it is, right? See, this whole procedure, except I had x's instead of p's. So here is the same equation from before. It's just, now we have p's instead of x, which means that when you go through this calculation all the way to the bottom, you are going to get your logistic equation, which has a, b, and then x. That x is going to be population, so p of t. And I mean, we already did this. I don't know if we want to do this and waste time. I mean, this is the class. There is nothing else in it. You learn logistic population, then we talk about the limiting, capacity for the population for any species. So the way this is solved, right, is we separate the variables as I did, and then we integrate both sides, and we use partial fraction decomposition on the left, and we use just a basic integration on the right. So over here we have a dp divided by, and I said that negative, right? We'll kick a negative out. Well, a minus bp times p equals to integral dt. And then you are going to swap this to look like your, so we'll kick the negative out, we'll put the p first, and then we're gonna go do bp minus a, right? Because I factor the negative, the parenthesis swaps. And then on the other side, you have now integral dt. This negative will jump to the other side. You have partial fraction decomposition here. And now this is all done. And so I'm not going to go further than this. dp over p bp minus, oh, you need to divide by b now. So it's going to be 1 over b. And it's going to be p minus a over b equals integral dt. And there's a minus there. So you sub this, maybe capital M or whatever, and so on. So done in 1.3 lecture. So we don't have to waste time and go through the calculation step by step again. You have the video from that time. Now I'm going to just dump the solution to this equation, and we're going to go from there. So a couple of more of these transformations. Calculation is exactly the same. dp dt equals what we had before, ap minus bp squared, can be transformed into dp over dt equal to k p m minus p, where k is b and m is a divided by b, from the equation here. So you can verify that these two equations are the same equation. Now this is the logistic equation. You can also add to it initial condition p of 0 equals p0. This is initial condition of population at 0 time, which is when you start measuring, is p0. So you are airdropping 500 rabbits to the island that has no rabbits on it, and you start measuring at that point in time, right? So it doesn't matter, it's 2020. It's your year 0 in terms of rabbit population for that island. So you are going to start measuring there, and you are dropping in 500 rabbits, so p0 equals 500, and that would be your initial population. Now, if you want to talk humans, you go to Google and just say world population or US population in 1973, and that becomes the year. You pick your year because you're doing some kind of research or something, and you just want to start somewhere. The calculation here is the same, right, as the one above. There's no difference. It's partial fraction decomposition all the way, and so 1.3 solution steps go here. There we go. See how fast I am and slow solving these things. And I would truly hope that you would take 30-40 minutes to do that, because that's your practice. I mean, this class is over in 10 minutes and, whatever. But your process of learning these things is going to be when you sit down and actually do these things again from scratch, so that you know how to do these things. You don't have time to look this stuff up during the exam. It's, 10, 11 questions, 90 minutes timed. So you don't have time on the exam to look it up and try to figure it out then and so on, because it's, 1 out of 10 questions or 11 questions, whatever. All right, so solution. For the logistics equation, once you go through the basic calculation I did, well, it's basic because it's partial fraction decomposition, basic integration, and then algebra. So we did not use any advanced mathematics there. It better be MP0 divided by P0 plus M minus P0 times e to the negative kmt. So this is going to be your solution to the differential equation. And what you find there is that the graph for that equation looks like this. I mean, no matter where you start, let's say you start at the initial population here, and the graph is going to go, let me first put in this carrying capacity M. And then your population is going to exponentially grow, and then it's just going to flatten out in time. So you wait sufficient amount of time. It's not going to grow forever like the first model we had. This one is going to level off and follow this point M, the carrying capacity. So M is known as carrying capacity, meaning this is the maximum amount of people or rabbits or whatever that environment given by the parameters can sustain. Now, those parameters I said, it's food, it's disease, it's predators, it's all of the stuff, that rabbits have to worry about in their existence. And for humans, the same thing. Now, for the same model, if your P0 happens to be bigger than M, guess what happens? Right? If you have the same situation, you have your M over here. If you graph a curve, it's just going to do whee, and it's going to drop down because the environment cannot sustain the population. So those who were not competitive enough to get the food and the resources, they die off, right? Same thing with jobs, right? One person that spent a lot of time practicing writing and speaking and public speaking and took communications class and 15 English courses, this person can put together amazing resume, can explain things very well. This person is obviously going to be chosen over charismatic and all that, is going to be chosen over the person that is 4.0 and the only thing this person did is just stared at the, a book and never actually practiced any of the skills and just did the, bare minimum of what the program said. I always say to students, you have to take communications class. I don't care what your major. At some point, you have to explain yourselves. At some point, you have to present the idea. At some point, you have to sell something. And without communications class, just good luck. I don't care what your major is. Without communications, you are going to be severely disadvantaged going into whatever your career is. And I really don't care, because all of the careers involve explaining what you want to do or your project or presenting your project or stuff. So you have to do it, right? So the same thing now, right? The way you would fall off the race for a job because you don't have communication skills and writing skills. even though you're doing engineering. The same way is for population, right? If the units of that population are not able to competitively, be competitive enough to get the resources and food, obviously they would die out. So the population still goes down to the carrying capacity which is set for that particular population. Now, scientists can't agree, with the population of the Earth. They can't agree, whether it's 15 billion or 10 billion or 12 billion. So the largest number I heard was 15.2 billion. The lowest was 10 something. I believe Professor Peterson said in one interview or something that it was like 9.7. We are at 7.5. All right. So what if it's 9.7? We have like another 10 years until we reach, right? And Corona did nothing in terms of population reduction on a planetary level. I mean, it's when you look at the amount of billions, I don't even know where the total is right now. Let me see, real quick. Worldwide. It's not even a million across the world, right? Not even a million across the world. So when you take a look at that, it's going to be, let me see real quick. So we'll do this in billions, right? So that's going to be 0.1 billion. Yeah. Way too many zeros to be significant. We do not, so the population did not adjust itself or anything as we are going towards this line, that it's the limiting population. Now, again, anywhere from 9.7 to 15.2, so we might be right close to it, or we might be, halfway through it. But with the exponential growth of population, I mean, whether it's almost there or you have to go 2 times as much for exponential growth, 2 times is just one step. So that's not a big deal. So we have also a case where you have a negative K. I did mention that before, and negative K means declining population. In the book will be labeled as extinction, right? So you are going to have, what we call endangered species that are, that we are protecting and try to save. Those have the negative births, right? And then we get involved, and they change the ratio into a positive birth. But at the rate at which the species are disappearing and the new ones are coming up, it's just what the natural state of thing was for millions and millions of years, hundreds of millions of years on the planet Earth. So I guess people feel good about themselves if they do that, so whatever, let them do it. But the way I say is, the extinction is just going to be the negative K. So if you have a population growth, is a positive K. And don't let this negative K fool you. This is growth model, because the negative K is in denominator. Remember, when the negative goes in the numerator, it becomes a positive, right? So negative in denominator means growth. Positive in the numerator means growth. Now, when I say extinction and I say negative K, I mean a negative K in the numerator. And that would be, right, going into time, and extinction means that species doesn't exist anymore, right? So dinosaurs, for instance, right? That species doesn't exist anymore. Like all of the species of dinosaurs, they're all gone. And we have their relatives, like crocodiles and stuff. Like that's direct descendant, right? Evolved from that time into the killing machine it is today. Shark as well. But other than that, we don't have many of those species that are close to what the dinosaurs were um, hundreds of millions years ago. Now, that's extinction, right? So you have that as well in the book, and you can look it up. So that was 2.1. Um, the Wednesday class is on equilibrium and stability of solutions. It's going to be a little bit theoretical and weird, so be ready for that. I always suggest you read the section to get pumped up and to go, what the hell, right? That's also that's very good attitude to have going into that. So probably pay attention when you go in. And the homework for 2.1, I am actually poking through the my MATLAB right now to open up the homework for 2.1 so you can practice that. And I hope to see you all on Wednesday. Have more fun and work on differential equations. So if you have any questions, stay on Zoom and go ahead ask, and I'll see you guys on Wednesday. Bye.